Hello dear friends, welcome to my channel. Today's discussions is very important for quantum mechanics learner. So today let's see the syllabus. Quantum mechanics 2, Schrodinger wave equations, expectation value, infinite square wave potential, finite square wave potential, and three-dimensional infinite potential wave, simple harmonic oscillations and barrier tunneling. So friends, I will discuss today three-dimensional infinite potential wave. Okay, simple harmonic oscillators and barriers tunneling I will discuss in my next video, because these two chapters I will discuss in another video. Okay, then I will complete this total chapter 6, and this is the important for this video is important for BTech engineerings, also physics graduates, and also masters. Both case, this video is very important. So friends, Richard Feynman told that I think it is a safe to say that no one understands quantum mechanics. So quantum mechanics is not so much easy; it is very tough. So it cannot, no one understands quantum mechanics. Do not keep saying to yourself if you can possibly avoid it. But how can it be like that? Because you will get down the drain into a blind alley from which nobody has escaped. Nobody knows how it can be like that. Yeah. So I think, I hope that you can understand what Richard Feynman want to say. Okay, so friends, this is very tough and difficult quantum mechanics. But however, I will try to complete the syllabus. So let's start expectations values. So useful to relate the wave functions to measurable quantities. In quantum mechanics, the expectations value is the expected result of the average of many measurements of a given quantity. The expectations value of x is denoted by x, is denoted by this type, this way. Okay, and conversely, for a single measurement, the expectations value predicts the most probable outcome. Any measurable quantity for which we can calculate the expectations value is called physical observable, and the expectations values of physical observable, for example, position, linear momentum, angular momentum, and energy, must be real. And because the experimental results of measurements are real, the average value of x in statistics, x bar is equal to ni xi divided by summation ni. Continuous expectations value. Continuous expectations value is the, we can change the discrete continuous variables to using probability p x comma f of observing the particle at a particular x. So friends, it is also discussed in my statistics playlists. Please check that, where you can, I solve a lot of problem based on these expectations. Okay, probability of expectations. So now I need to discuss that in quantum mechanics, the probability of quantum mechanics px is equal to mod of psi whole square equal to psi into psi. So the expectation value is x. This is the x, expectation value is x, and minus infinity to infinity x psi x comma t, psi x comma t divided by psi star. Psi stars means conjugacy. Okay, conjugacy psi xt. Okay, so I get this value, and if wave function is properly normalized, the expectation value becomes Normalized means this value is 1. Okay, lower value is 1, so expectations become minus infinity to infinity x into psi star x comma 2 x comma t psi x comma t. Now the expectation value of any function gx, normalized wave function, is gx equals to psi star x comma t gx and psi x comma t. This is the very basic but important for learner. And x is equal to x into psi star x comma t psi x comma t. A particle is described by the wave function psi x. Example, students, ax, and where x equals to 0 and x equals to 1 and 0 elsewhere. So how can I find out? Because psi star and psi is dx is equal to 1. So a equals to root over 3. This is the problem. And find the probability p is equal to 0.45 to 0.55 mod of psi square. Okay, is equal to a square into 0.45 and 0.55, and I get this value. Okay, the particle which probability I have to find out, 0.45 to 0.55. So friends, I find out this value. A square value is root over 3. So easily find x. Find x is equal to psi star x, x psi x, a is equal to 0.75. Okay, very simple. Momentum operator. Suppose we want to find expectation value for a momentum p. So p is equal to psi star x comma t p psi x comma t dx. And but what do we insert for p? We need a momentum extractor that represents p in such a way that we can evaluate p. Given the variable of integration is x, the extractor should be expressed in terms of x. If we start with the wave functions of a free particle, this wave function can also be written as psi x comma t a t into e to the power I t x omega t, and where psi x comma t is equal to a into e to the power minus I p x e t divided by h bar, where p is equal to h divided by lambda and hk divided by 2 pi h bar k, and e is equal to hf is equal to h omega divided by 2 pi h omega. I hope it is clear. Yeah, I hope it is clear, because omega is equal to e divided by h bar. Okay. Next, momentum operator p bar is equal to minus I h bar del by del x. How do we extract p from wave functions? Wave functions, if we take derivatives of the wave functions, the particle with respect to del psi x comma t divided del x into del a e to the power I p x e t divided by h bar, and I p h bar psi x comma t is equal to I k psi x comma t, and rearranging p psi x comma t is equal to I h bar del psi x comma t divided by del x. The quantity on the right has extracted the momentum of the wave functions. The extractor is defined to be the momentum operator p cap is equal to minus I h bar del divided by del x. And using operator, the expectations value momentum is psi star x comma t p cap psi x comma t, and p value just p cap means this is the momentum operator. Momentum operator p cap is equal to I h bar. So I am putting this operator. I get r minus I h bar psi star x comma t psi x comma t del x into dx. So energy operator is equal to E h bar del by del t. Energy operator is able to extract the energy of the particles. The time derivatives of the free particle wave function is del psi by del t is equal to, this is my equations, and omega is equal to E divided by h bar and E psi minus I omega e to the power I kx omega t minus I omega psi. So del psi divided by del t. So therefore we can also define the energy operator. E cap is equal to I h bar del by del t. So the expectation value of the energy is E h bar del psi star x comma t del x comma t into del t into dx. Determine expectations value for p and p square of a particle in an infinite square well in the first excited state. This is the infinite square, friends, where En is equal to n square pi square h square 2m l square psi 3 psi norm of psi 3 whole square psi 2 norm of psi 2 and psi 1 norm of psi 9. This is the positions. So friends, the first excited states correspond n equals to 2. Therefore psi 2x is equal to root over 2l sine 2 pi x and Pn is equal to this equation is equal to 0. The answer mean particles is moving left as often as right. Okay, Pn means momentum, and for p square I get 4 pi square h square divided by l square p square, and comparing with E2 is equal to this p square is divided by 2m. Finite square well potentials. The finite square well potential is Ex is equal to, here you see region 1, region 2, region 3 and V zeros, and 0 to L, and this is the E. So Vx is equal to V0, 0, V0, x less than 0, region 1, region 2, region 3, and outside the well, region 1 and 3, Schrodinger equations is minus h bar square divided by 2m 1 by psi d square psi dx square E minus V0 regions 1, 3. Consider a particle with energy E less than V0 classically bound inside the well and define alpha square is equal to m V0 minus E divided by h bar square. So d square psi divided by alpha square psi, and I get these solutions with the help of differential equations. Please check my video, partial differential video, how to find out, because I have to find out m square is equal to alpha square. So m is equal to plus minus alpha. So I get e to the power alpha x and e to the power minus alpha x. Okay. Finite square well solution. Psi 2 is equal to c into e to the power I kx d e to the power minus I kx, and a into region 1 you see c psi 1 is equal to a e to the power alpha x, psi 2x is equal to b into e to the power alpha x. This is the potential level, energy equals to E. And now apply the boundary condition. Psi 1 is equal to psi 2 del psi 1 divided by del psi 2 del x is equal to 0. Del psi 2 is equal to psi 3. So del psi is at x equals to 3. So application not the straightforward. So we just show the results graphically. Wave functions. This is the wave functions. So you see psi 1, psi 2, psi 3, and this is the exponentials. And as in with the infinite well, the results of quantized energy levels En, energy E1, E2, E3, this is the energy level V zeros. And note, in finite case, the wave functions is non-zero outside of the box. Other differences: wavelength is somewhat larger for finite well because the wave function extends beyond the well, and this leads at a smaller momentum, slightly lower energy levels. For a finite well, number of levels is limited by the potential height V0. Define the penetration depth del x as the distance outside the potential well, where the probability significantly decreases. Del x proportional to 1 by alpha h bar divided by root over 2m V0 minus E. Penetration depth deeper as E approaches V0. It should not be surprising to find the So penetration depth deeper as E approaches V0. It should not be surprising to find that penetration's distance that violates classical physics is proportional to Planck's constant. Actually, detecting particle in classically forbidden region difficult. Del x is proportional to del x small, implying del p and thus del k proportional to h bar 2m divided by del x too large. No experimental could be certain the particle has negative k. Finite wave exponential. The condition is psi 1, psi 2, psi 3. Infinite wave psi 1, psi 2, psi 3. Three-dimensional infinite potential wall. In three-dimensional, the wave function is a function of all three spatial coordinates psi x, y, z, and in three-dimensional time independent Schrodinger wave equation takes on the form E is equal to k plus v p square by 2m plus v, and p square by 2m psi plus v psi is equal to v psi is equal to p square is equal to px p square x px y square pz square. You know that I have already discussed it in my channel in various video like string theory, Gordon quantum field theory, where I have already discussed these equations. Px psi is equal to I h del psi del x, and p psi py and I h bar del psi del y, and pz psi is equal to I h bar del psi by del z. So h square divided by 2m minus del square psi y square del square psi del square plus v psi is equal to v psi is equal to h square minus h square by 2m del square psi plus v psi equals to e psi. So consider a free particle in a 3D box, dimension L1, L2, L3. Find the wave functions and energies. This is the L1, L2 and L3. So particle in 3D box solution. Given the fact that the particle is free inside the box x, y and z, dependent parts of the wave function must be independent. So I use psi x, y, z equal psi x, y, and z, the method of separations variable. A reasonable solutions is equal to psi x, you can get the method of separation variable. And psi x, y, z is equal to x equals to 0, L1, then N1 pi L1, K2, N1, N2 pi L2, N2, N3 pi L3. Okay, all is the differential equations, and if particle is constant 3D, three quantum number N1, N2, N3 are required to describe the state. Particle in 3D box solutions continued. Psi x, y, z is equal to this n pi ln, and to obtain the energies plug wave function into 3D wave equations. H square by 2m minus del square psi divided by equals to E psi is equal to H square, del square means k1 square plus k2 square plus k3 square is equal to E psi, and k1 square plus k2 square plus k3 square is equal to a pi square h bar square. This is the formula. E, this value is equals to equivalent to E. So allowed the energies are defined three quantum numbers n1 square, n1, n2, n3, where the ground state corresponding n1 is equal to n2 plus n3 is equal to 1. So L1, L2, L3 is equal to L. So E n1, n2, n3 is equal to pi square h bar whole square 2ml square n square n1 square plus n2 square plus n3 square. So friends, this is my diagram L1, L2, L3. So friends, I have already discussed 3D box. Okay, now I discuss 3D box degeneration. That psi x, y, z is equal to a sine k1x, sine k2y, and sine k3z, and kn is equal to nn pi divided by ln. So E n1, n2 is equal to this value I have already getting, and the state degenerate that you see the diagram 2 1 psi 2 1 and psi 1 3. wave functions of 2D boss state degenerate. Okay, so a quantum state is degenerate when there are more than one wave functions for given energy. E211 is equal to E121 and E112. Okay, so this is the example, and degeneracy results from particular properties of the potential energy function that describes the systems. A perturbations of the potential energy can remove the degeneracy. This is the most important. A perturbations of the potential energy can remove the degeneracy. Degeneracy results from particular properties of the potential energy function that describes the system. So friends, this is the three-dimensional degeneracy. I hope I can clear the total quantum mechanics and I discuss everything and you can get a proper idea. Thanks for watching.